Welcome everybody on tutorial 4 of our day on extremes and variability. We'll now look at return values again. We already did this in tutorial 2, but then we based it on empirical data, but now we're going to use our distributions that were fitted to empirical data. That will give us some advantages of the previous method that I hope you'll really like. But first, a little bit of a recap from tutorial 2. The most important thing that we learned there is about these X-year events. For example, we just had a precipitation record. Let's look at storm events. So what were those again? Say that you have a 100-year storm. That means that that storm has a 1% chance of happening in each year. Practically, that means that we expect to see that storm at least once every 100 years. It could happen more often, could happen less. You expect to see it every 100 years based on those probabilities. 2-year storm would have a probability of happening in each year 50%. We would expect it at least every 2 years, the 2-year storm. We can compute those return levels and return periods from our data directly. We did that before, however, that wasn't perfect. So now we're going to use what we call the cumulative distribution function, property of our distribution based on our data set or our parameter set that we fitted from our data. This is how that looks like for any random set of parameters. It's always this sort of C or S-shaped graph where it starts out pretty flat, then rapidly rises towards 1 on the y-axis and then flats out. The y-axis, you see, the variable is probability. That probability is the probability that a random value of our variable, for example, precipitation here, is less or equal than a fixed value of our precipitation or of our variable. So in this case, precipitation. So you see that the further you move towards the right, towards higher values for precipitation, the bigger the chance becomes that a random value will be lower than that. That makes sense because more extreme precipitation values are not happening that often. So the chances are that the next year will be lower, or the next 2 years, for example. Hopefully you understand, based from what I've been saying so far, that this is the opposite of the earlier mentioned exceedance probability. The exceedance probability being the probability that a random value will be higher than some value of our variable. In this case, it was lower. We can use that to our advantage. For example, if you look at this graph and we take 40 millimeters a day as our precipitation thing, we see that the probability of that is 75 or 0.75. So there's a 75% chance that an annual maximum event is less or equal than 40 millimeters a day. Again, it's the opposite of the exceedance probability. So if we switch that, we say that we have 25% that an annual maximum event is 40 millimeters per day per year. That 25% means that we can at least see it, that we expect it to happen at least every 4 years. So 40 millimeters a year is our 4-year event. We have just computed return values and return periods from our cumulative distribution graph. And again, that graph is based on our on a parameter estimation from our data set. So this is the method that we are going to discuss. Basically this, we're going to do that for each of those values based on these two simple formulas that we have also used for our empirical distribution. So if we want to know the return period and we have an exceedance probability, then we can use the formula 1 divided by 1 minus our exceedance probability. Or if we have a return period and we want to know what the exceedance probability of it is, then we can do 1 minus 1 divided by the return period. For example, for a 10-year flood, or if you want to know the 10-year flood, that will be P is 1 minus 1. Or if you want to know the 10-year flood, 0.9. So what we can do is we can compute all the return periods for the values on our x-axis, our return values. And then we get something like the following graph. So this is our return level and return period graph. We just did exactly the same steps as we did before with our little thought experiment when I went through it. Here you see that it's a pretty straight line. That's because I used a log scale on the x-axis. So normally you would have the same line shape as we saw with the empirical distribution, a log shape, but in this case it's on a log scale, so it becomes a straight line. Unlike with the empirical values, we can actually extend that line to, for example, 1,000-year return period, which is something that you might want to know if you're working with very delicate infrastructure projects, or if you really, really want to protect a city for a big event. So here you can see that the 1,000-year storm, for example, is 87 millimeters a day. So that's something that could be helpful. One thing you should take into account, though, is that we only knew very little about these extreme events, right? Because they're based on very little data. So there's a lot of uncertainty around these values. We can compute those as well by computing the confidence intervals over our parameters and then plotting the same type of lines. So again, we are estimating from the data our parameters for a GV or a normal distribution. So if we want to know the confidence intervals, we have to look at the confidence intervals of our estimated parameters. And based on that, we can then, for example, make the similar lines. And here you see that we are much more certain about our lower return periods, again, because for those we have more data. We are very uncertain about the larger return periods, for example, 1,000-year floods, because we have very little data for those. One way of reducing that uncertainty is, for example, by extending our data through either paleo data, like there's a lot of climatologists that use paleo data, or perhaps other statistical methods that you can find. Now, go into the exercise and try to fit a GEF distribution yourself, and then compute return levels from that to see what it is like and how it compares to, for example, those of the normal distribution. See you in the next tutorial.